Ready, Miss Sharif? Is that a yes? Okay. Keplers laws. Okay, you got this? No? Yep, Keplers laws. Okay. So, Kepler has 3 laws, and we're going to look at those 3. First one, Kepler's first law for planetary motion. Kepler's first law states that bodies in orbit of the Sun, now of course for Kepler at the time there was only the Sun, but it's not just the Sun, it's anything like it. Bodies in orbit of the Sun or other large masses will move either in a circle or elliptical path. So far we've said that motion around a star or a planet is in a circle, and that's true, but a second possibility is an elliptical path, which is an orbit that looks like this. And you can actually prove this using Newton's law that we did yesterday. However, at the time Kepler didn't have Newton's law because Newton wasn't born, but we could prove it now that this law is a result of Newton's formula from the last class, that the orbit is elliptical, which kind of means it could have this egg shape to it. It's not quite circular. So I think it'd be great if you can draw this as well as the definition. Yes? Okay, continue. Continue?
Yes.
Yeah. So, that's Keplers first law. The proof of this is actually too difficult for us to do, so we won't prove that this is true. Okay, Kepler's second law now states that, do you know what? We can prove Kepler's second law, but actually I'll give it to you first, but don't write it down just yet. The periodic time squared is proportional to the radius cubed, or as a formula it can be written like this. This is Kepler's second law. Now, warning, I'm going to prove this now, and this is one of the 3 proofs on the exam. Yes, this is the last proof. The proof of Kepler's second law. So, you don't have to write it down right now because we're going to prove it now. Okay, so the idea is you have a large planet body of mass m and a small body of mass m. And this is kind of like real life. In real life, you don't know the masses because you can't see the masses. When you look at this in a telescope, the only thing you could work out from the telescope is the distance between them, using some trigonometry, and by just using a clock you could work out the periodic time. So for example, the Earth is 365 days to orbit the Sun, the Moon is 28, 29 days, and so on. So, let's use a couple of formulas here. From circular motion, we have, from Newton's second law, we have F equals ma. That's one formula we need. But Newton also tells us F equals gm over r squared. And also from circular motion, F equals m omega squared r, and t equals 2 pi over omega. So I'm going to start this by trying to imagine getting a formula for t. So you could say t equals 2 pi over omega, but we don't know what the omega is, so we can get the omega from the previous one. 2 pi over f over m over r square root. So what I've done is I've rearranged this to get omega, f over mr square root. Okay, which is equal to 2 pi root mr over f, which is equal to 2 pi root mr over gmm over r squared, which is equal to 2 pi root mr cubed over gmm. So the small m's cancel, and if I square both sides, I get t squared equals 4 pi squared over gm times r cubed. And this is Kepler's second law. And the reason this law is so important is because the 4 we know, the pi we know, the g we know, the t we can easily know, and the radius we can easily know. So it gives us the way to calculate mass of planets by simply looking at how long it takes the moon to orbit that planet and the distance between the planet and the moon. So Kepler says that basically we have a formula to calculate mass. The only requirement is there must be something orbiting that mass. If there's something orbiting that mass, then we have a way of knowing what the mass is. Or likewise, but unlikely, if you knew the mass and the radius, you could work out the time, the periodic time. But I find that most situations it is the mass that is the thing you don't know and what we want. So like I said, this is Kepler's second law, and this is one of the 3 proofs that they tend to ask in the exam.
How though, like practically, how knowing the orbit and the distance between the masses gives me the mass?
Well, there you go. We just proved it there.
Okay, so the formula, right? But that's because we know the formula. Right?
Yeah.
How did he figure it out?
He figured it out by looking at lots of data. And in fact, I'm slightly not being accurate to what Kepler did. Kepler never actually got this particular formula because this formula has something in it which only Newton at the time knew. Kepler's formula was just this one, that t squared is proportional to r cubed. Kepler did not have this constant in his formula, and he got this by looking at information, times of orbits, the distance between the planets and the sun, and he noticed that if you square this and cube this, then they'll be proportional. But even that is not obvious. If you square this column and cube this column and plot it, you'll get a straight line. But like I said, that's not obvious from just looking at it. So this really is maybe the original version of Kepler's second law. But because of Newton and because we know our circular motion formulas and this formula here and this formula here because of Newton, we can actually improve Kepler's second law and give it as a formula, which makes it much more useful then. But we call this Keplers Second Law. And like I said, this proof is on the exam. And not only is it on the exam, it is in section A and in section B. I've seen it in both. It is not the most common. It's tied with the one with the E and the log in it, if you remember, for the the RC one. Yeah.
Can we count the log for the
Yes, if you memorize it, you can. Oh yes, thank you. This formula is not in the book. Not in the book.
I mean now, can we write the law? Just
Can you use the law in question?
in the slide.
Oh yeah, well this is the law here. Yeah, it's a formula. These two here, you should read. This is Kepler's law, or it can be written like this, except this one is the useful one. But you need the proof. The proof's on the exam. You heard me say that, didn't you?
Yeah.
Oh, good. Got that? Keplers Second Law. So, to be anybody, you need 3 laws. So we'll have a look at the next law. Keplers Third Law states that the area swept out by an orbiting body per unit time is constant, which requires more explaining. So, first I'll just draw exactly what that means. Imagine we have the Sun here, and we have the Earth in an elliptical orbit, or well, whatever planet we have here. And we look at days, or months. We'll look at months. So, in 1 month, the Earth moves from this position to, let's say, this position. In 1 month, let's say 1 mt. If we calculate this area, let's call that area A1, and then look at the next month. Now, because it's elliptical, this distance here is shorter, correct?
Yeah.
But what Kepler discovered is that if you calculate the area drawn as it moves, we'll call that A2, the areas in fact stay constant per unit time. So although you might think it should be getting smaller, it stays the same. So the reason for that is because it must have moved a greater distance to keep the area the same. This is Keplers Second Law. So what's happening to the planet here compared to here? Well, it must be moving faster here than here, so that it can keep the area it's drawing constant.
That's why.
Yeah. Don't know actually for the moon, because I think the moon's orbit is pretty circular, which means there's not much change in the speed. I don't know. I suspect the reason might be more likely because there's maybe 28 and a half days, and sometimes you round up and sometimes you round down. I don't know. So that's what it is in words, but as a formula, you can actually show that, well, as a formula you can state it a couple of ways, but the ones that's most useful to us is that V1 R1 equals V2 R2, where V1 is the velocity at the start and V2 is the velocity at the end. R1 is the radius at the start, R2 is the radius at the end. So in this picture here, this one could be R1 and this one could be R2, and the speed here could be V1 and the speed here could be V2. So, can you see, if it's moving in a circle, what do we know about R1 and R2?
Same.
The same. So then what do we know about V1 and V2?
Same.
So in circular motion, the velocity doesn't change. V1 will equal V2.
Can you say that it moves faster?
Yeah, but that's because it's an elliptical motion here. If this was actually a perfect circle, the speed would stay the same because the radius is staying the same. And here actually, this is the example we just drew as well. So Kepler said the area here and here is the same. This proof is not on the exam or on the course even. Okay, so a couple more definitions here. Geostationary orbit, also called the parking orbit. Does anyone know this term? I don't know if you've heard it before. So, for Earth, a geostationary orbit of a satellite is a satellite that takes 24 hours to travel around the Earth. So, in other words, its orbit around the Earth or another mass has a periodic time of 1 day. Now, that's for the Earth, it's 1 day. But of course, it's the same definition for like Mars, except maybe a day is longer on Mars or shorter. I don't remember. I think it's longer. Why is this important? Well, if you think about it, if you have the planet and you have a satellite above it, how long does it take the Earth to turn around on its axis completely? 24 hours. And if the satellite takes 24 hours to orbit, what happens is the satellite moves with the Earth. So the effect is, if you're standing on the Earth under the satellite, it appears that the satellite is always above you. Hence the word parking orbit or stationary orbit. So these are important for GPS satellites because GPS works in a way, the GPS system works because all the satellites are in stationary orbits. They always look like they're in the same position. You got that? Yeah, continue. You got that, Mashif? So for Earth it's 24 hours, but for other planets, of course, it's different. Right, we'll have 2 questions here. A small satellite is in parking orbit around the Earth. How far is it from the surface of the Earth? Note that the radius of the Earth is this and the mass of the Earth is this. So we could use Keplers Second Law here. We know the time. What's the time? 24 hours. We convert it to seconds. We know the mass of the Earth. I give it to you. And what am I looking for? The radius. The or, yeah. We do not have the radius of the orbit. We have the radius of the Earth. Not the same thing, of course. So I'll just give you a minute to try this one, but you're just using Kepler's second law here.
And the D is 24 of
In seconds though.
Yeah.
Yeah, 3,600 times 24.
How do we know the radius of the information? We have the information.
Say again? We have the T, we have the M, and we can get the or from Keplers Second Law.
Yeah. But I mean, the T is for Earth, the G is for Earth, the M is for Earth. Okay.
The T is for the satellite, which is the same as for Earth because they're in a parking orbit.
So this is the satellite.
This is the satellite's T, and it's the satellite's radius, but it's the Earth's mass in the formula. We've got an answer.
Okay, it's C squared and R cubed.
Yeah, so you'll have to cube root, because you want the or, basically.
Oh, so I treat it like it's just C. It doesn't make a difference that it's C squared.
Well, you have to square the T, but...
I squared the T and then divide it.
And then cube root it, yeah.
3.16 times 10 to the minus 5.
Now, that makes it extremely close to Earth, 10 to the minus 5. Because an orbit of 10 to the minus 5 would be on the ground. What's Kepler's law here? T squared equals 4 pi squared over gm or cubed. So that means gm over 4 pi squared t squared equals or cubed. So or is the cube root of gmt squared over 4 pi squared. But remember please, that is the distance from the center of the Earth to the satellite, and we want the distance from the surface of the Earth to the satellite. Minus what's it, 6371?
Right?
The distance we have found will be the distance from the center of the Earth to the satellite, but we actually wanted the surface of the Earth to the satellite, so our answer will be a tiny bit too big. We'll need to subtract this from it. But let's hit it in on the calculator, which I need to actually open. Let me just put in the numbers while it's loading. So the answer will be cube root all over 4 times 3.141592654 squared, and then 6.67 times 10 to the minus 11 times 5.97 times 10 to the 24 times, with a square here, 24 times 3,600 equals.
Can solve it without taking the square root.
What do you mean?
I can't take
The cube root?
yeah.
By a Casio calculator. You have an answer? It should be big enough.
35.8 negative.
Yeah, that sounds kind of like it. Let's just hit it in here. Where's the cube root? Cube root fraction 6.67 times 10 to the power of minus 11 times 5.97 times 10 to the power of 24 times 24 times 3600 squared all over 4 pi squared minus 6371000. Pretty big. We'll put in kilometers that seem most suitable. So 35,900 kilometers. 35,900 kilometers is the answer here. Okay, next one. Next one. So, next example, one more to do. The planet Mars is observed to be on average 228 million kilometers from the Sun. One Mars year is actually 687 Earth days. Using this information, calculate the mass of the Sun. Hint, you may assume it's a circular orbit. So, in other words, nothing fancy at the beginning. Just use Keplers Second Law to get the mass of the Sun. Okay, so just do the A part first, please, and then we'll look at the B and C separately. So, let's see, do you have the T? Yes, it's 687 times 24 times 3,600. You have the T. Do you have the OR? Yes, you do. It's 228 times 10 to the 6 times 10 to the 3 meters. And what are we looking for? We're looking for the M. So, Keplers Second Law again. Okay, let's have a look, see here.
In the previous example, we, like, I still don't understand completely how they did it. Because most of it is constant.
Yeah. Well, let's do another example. So, this is Kepler's formula, yes? What are we looking for in this case? M. So, I'll just rearrange it to get the M. So, I bring the M up and the others down. So, I have 4 pi squared or cubed over g t squared. The 4 we know, the pi we know, the radius I give you, the g we know, and the t we know. So if I just take out the calculator and just hit everything in, on the top I have 4 pi squared, and then the radius cubed, and what did I say the radius was? 228 million kilometers over gt squared. And the t here is 687 times 24 times 3,600. That's the time in seconds. So we should get a big number for the mass of the Sun, and we do, and this is right. If you look it up on Google, the mass of the Sun is about 1.99 times 10 to the 30. So the answer for the first part is 1.99 times 10 to the 30 kilograms. B now. What is the velocity of Mars? So, because it's circular motion, we have the circular motion formulas we could use. What would be the easiest one? We have A equals V squared over R, so we can say V is square root A R, which is square root A is F over M. Yes, F over M, which is good actually. Well, is it? Do we know the mass of Mars? We don't, but that's okay. The A is F over mass of Mars times the radius. But Newton gives us a formula here for F. He said it's G mass of the Sun, mass of Mars, over R squared, over M, or. So we can do a bit of cancelling here. And actually that square cancels with that because this is on the top. So it'd be square root Gm over R. The mass of the Sun we now know, and the radius we already knew, and the G we already knew. So if I just take out, I'll leave my answer on the calculator, and it's square root fraction 6.67 times 10 to the power of minus 11 times my answer over, what was it, how many million? No, the distance. 228 million. So it should be going pretty fast, and it is. We'll put in kilometers per second. 24 kilometers per second. So our picture is when it's what was it, 288 million? Yeah, 228 million megakilometers. When it's 228 million kilometers from the Sun, its speed is 24.1 kilometers per second. Now, when it's closer to the Sun, will it be going faster or slower? Faster. So the next part is when it's 207 million. It should be going faster. We'll call it speed V, and V is what we want. So we have the formula V1 R1 equals V2 R2. So I'll call this like V2. So I get V2 equals R1 over R2 V1. Now I don't have to worry about the units because they cancel. So it's 228 over 207 and the units cancel. And the V1 is 24.1 kilometers per second. So this answer will be in kilometers per second. So if I multiply this by 228 and then divide it by 207, about 26.6. So it'll be going faster, it'll be going 26.6 kilometers per second. Okay, so if you can write this one down, please.
Can you scroll up?
Yeah. Yeah, continue.
Yes.
Yeah. So, just one question. Just to put this into perspective, this would be like a section B question. From an observatory on Earth, Mars is observed as having two moons. One of the moons, called Phobos, is observed as orbiting Mars at a distance of 9,000 kilometers, and its orbit takes 7.5 hours about to complete. So that's one of the moons, called Phobos. Finally, the radius of Mars is also estimated to be about 3,000 kilometers. NASA is planning on sending a small 100 kilogram probe to Mars. Help NASA by answering the following. You may assume a circular orbit when necessary. One day on Mars is known to be 24 hours and 40 minutes, so about the same as Earth. So the first thing you need to do from your observatory is estimate the mass of Mars. How fast is Phobos moving around Mars? And so on. So we'll leave this one as your homework and we'll do it in the next class. But everything here is, this is very much what a section B question could look like in the exam because of its multiple parts. Yeah? Alright, we'll leave it there. That's it, yeah. You want to take a picture of it? Go ahead, yeah. Got it, yeah?